Good afternoon, everyone. We'll be starting class in 1 to 2 minutes time. In the meantime, it would be appreciated if any of you can tell me if you were able to access quiz 1 and see your results or any individual feedback, because I'm not sure if I need to toggle any of the settings on quiz 1 for you guys to see this. So please let me know in the chat so that way I know after today's session if I need to change the settings or not. Okay, thanks. So I'll make a note here to know that I need to change those settings so that way you guys can actually start seeing the feedback for quiz 1. Alright, good afternoon everyone, and in today's session what we're going to be doing is the two important topics regarding our advanced data structures, which are going to be trees and graphs. And what we're going to learn in our first session regarding trees is going to build regards to what we're going to be doing in graphs in our second session. So if there's anything that you don't understand in trees, please make sure to ask during the lecture, and feel free to interrupt me because you are going to need the knowledge from trees in order to understand graphs more effectively. So like I said, feel free to interrupt me if you don't understand something in trees because you need this knowledge in order to understand graphs in our second session. Now, we have already seen some sort of trees in our previous lectures in some sort of fashion, and in particular we might have seen the binary tree where we saw the nodes and the nodes spanning with multiple nodes. We saw that each parent node had 2 nodes and so forth. What we're going to see here in this lecture is what's going to be the terminology for describing these trees, as well as our formal definition and any algorithms that we can use for actually traversing our trees and sorting our data accordingly regards to them. And then when we move on to graphs, which is basically like a more fancified version of trees, we also see like how we can do certain things with graphs and what its applications are for, and how we can use different algorithms to go about doing operations on the graphs and finding certain data and so forth. And you'll see that basically trees and graphs, which are our advanced data structures, actually are very important for a lot of stuff in software design because there are very optimized ways of sorting and handling data as well as searching for data within any sort of organized data scheme. Alright, so let's get started. So trees basically, they are a little bit tricky to understand. And searching throughout them is a little more complicated than your standard array or linked list because of their arrangement. And it may seem a little bit difficult at first, but once you start understanding how the layout is and how it actually operates, it becomes a lot more simpler to go about using the trees in particular. Depending on the tree itself, because there's no standard structure for any type of tree, the worst case and average case, regards to its space and time complexity, actually can widely vary. So it's very implementation dependent for determining the worst case and the average case. However, the way you go about implementing each one of these, once you understand how to implement one, you can implement any other type as well, because the understanding is basically the same core concept that you start with. So a tree basically is like a fancified node data structure, where each tree has a root node where everything starts from. This root node can have no children or multiple children, which we refer to as child nodes. And each child node can also have no children or multiple children and keeps on spanning, such forming the leaves of our trees. Now, one thing to note is that, like any general tree which you may think or you may physically see, trees themselves cannot contain cycles. So there's only one directional data flow that you basically kind of observe throughout the tree, and there will be no loops between nodes as a result. Nodes in a tree, they may or may not be in any particular order. They may not also link back to the parent node, and they can have any sort of data type as their values. Meaning that once we start physically seeing what this looks like in a visual format, all these explanations here will match back to what we just explained. So if we consider the root node here being our starting node as the value 10, we're able to split this into a left subtree and a right subtree. If we draw this accordingly, so this side here would be our left subtree, and this side here would be our right subtree. And this is with respect to our starting node here, which is root node 10. So anything here that's on the left subtree would be these nodes that are the left of our root node. So it would be 5, 1, and 6. Similarly, anything for the right subtree will be anything to the right-hand side of our root node, which will be 19 and 17. Now, note the order in which I'm going in. I'm going downwards by counting each node here at their appropriate levels and then moving to the next levels. And this is going to be somewhat important as we keep on going on through explaining how trees operate. The other thing to note is that in the left subtree here, all these elements are less than 10. And in the right subtree, all these elements here are greater than 10. Similarly, if we watch for one of these children nodes, so if we are watching at 5, the child node of 5 here, which is 1 on the left hand side, is less than 5. And the child node of 5 here, which is 6 on the right hand side, is greater than 5. So this particular order we see throughout, representing our trees in particular. Similarly, 5 and 19 here are children nodes of 10, which is where 10 is also referred to as the parent node. And 1 and 6 are children nodes of 5, where 5 is the parent node of these two nodes. 17 here is also a child node of the parent node 19, and so forth. 1, 6, and 17 here are referred to as leaves because they have no further existing connections linking to other nodes throughout except their parent nodes. So any leaf that you see in a tree has no children nodes. So basically this represents the end of our tree as a result. A level in the tree basically means nodes that are at the same depth. So basically I can say the same depth here being the same horizontal level. So I can say this here is at level 0, this one here is level 1, and this one here is level 2. The height of a tree is going to be the longest downward path from a node to a leaf. So it can be from any node here to any leaf that you have within the tree. So if we say what's the height of node 5 here, this would be from 5 to any leaf here. So that height here is going to be a difference of 1 level, so that's going to be what? If we say what's the height of 10 here, the height of 10 here is going 1, 2, is a difference of 2 levels, so that height there is 2. So that's the height of a node in the tree. The height of the overall tree would be from the root node to a leaf in particular. So the height of this entire tree here is going to be a difference of 2 levels. So we are 0, 1, and 2. Are there any particular questions regarding this terminology so far with respect to trees? No, a tree does not only have 3 levels. This is just for an example. A tree can actually have multiple levels. So this is just a simple example to illustrate the terminology that we're seeing so far. But it's possible for trees to have like 10, 20, 100 levels, thousands of levels, and so forth. Because trees themselves can actually get very complicated in their data structures. And that's because your trees themselves, they don't have any standard format regarding their analysis. They can actually have multiple children nodes instead of just 2. They can have 3 or 4 children nodes and so forth, and they can keep on spanning infinitely or keep on spanning towards some huge number. So it gets very big, but once you understand the terminology and how they operate, it doesn't matter how big the tree is. It's basically going to be the same sort of methods you will use to go about operating on the tree itself. So once you understand how one tree operates, you can apply it for any sort of tree that you will encounter. So you know when you reach the leaf, because if you start from your root node and you keep on going and then you can't further go anymore, these nodes where basically you can't go any lower, that will be basically your leaf. So your leaf will be at the lowest possible level, or when you can't go any further levels from a node itself. Alright, any further questions on our terminology here? No, a tree can actually contain any sort of data type which you require. And that was in the starting slide. So it doesn't necessarily need to contain numbers. It can contain decimals, it can contain characters, it can contain strings, it can contain vectors, it can basically contain any sort of data. I'm just using numbers here to make the explanation a lot easier. Yeah, sure. So the height of a node in the tree is that you select any node within the tree and then you go down towards a leaf, and the difference in levels would be the height of that node. So if we try to find, okay, let's say the height of 19 here, we go from 19 to any available leaf that is connected to. And we see here that, okay, the leaf here is 17, and this is at level 2. And the difference in levels here will give us the height of 19, which is 2 minus 1, which is just going to be 1. If we wanted the height of 17 here, because 17 here is already at a leaf, then there's no height here, so the height here is just going to be 0. Similarly, if we said we wanted the height of node 10 here, we can go from 10 here towards any direction towards any available leaf, and then we just do the difference in levels to figure out what's going to be the height. So the height of root 10, this node 10 here, is going to be from 10, so that's level 0, then level 1, level 2, where it can be any leaf here, and then just 2 minus 0, which is going to be 2, regarding on the height of our node here. So the height of a node represents any node within the tree towards any leaf that it is connected to. The height of the tree would be the longest path you can take from the root node towards an available leaf. So basically, your direction of the tree here, it goes down. And you'll be starting, so this will be like your start. And then any of these here will basically be like your ends, because these here are your leaf nodes. The start here is like your, oops. Do that? No, I can't. Alright, so don't worry, I'll draw it back. So, your start here is like your root, and then your end here are your leaves. And then that was level 2, level 1. Let's say it was level 0. So basically, the height of a node is any node in the tree towards an available leaf. The difference in levels will give us the height. And the height of the tree will be from the root node to any leaf node where you can take the longest path available. So for instance, let's say, and I'm just illustrating here, just to explain this, if this 17 here connected to some other node, and let's call this 8, then the height of the tree here would be the longest path you can take, which will be from here, which will go this way, and here, and then here. And at this point, this will be at level 3 for this node. So the height of the tree here will be 3, being the longest path you can take from the roots to a leaf. Right. Any further questions? Alright, doesn't seem like we have any further questions at this point. Alright, let's move on. So, if you're writing your tree class here, it's a lot easy to write this because you just need to have a node structure or a node class, and then the tree class will be responsible for handling your nodes. And it's very similar to how your linked list class structure operated, where you had a struct for your node, and you had a class for the linked list. We can also use a struct here instead of a class for the node, and that's not a problem. But if you wish, you can just use classes for everything throughout, and it'll operate the same way regardless. Now, there are different types of trees that you will encounter throughout any computer system that you will be using. Typically, the most common one you're going to encounter is going to be the binary tree. And a binary tree basically means that each node will always have 2 children at most. It will never have more than 2 children. It can have 0 children, it can have 1 children, and it can have 1 child, sorry. And it can have 2 children, but there will never be 3, 4, 5 regardless. And it can basically, that behavior gives us the terminology for it being a binary tree. Now, there are other types of trees, like if a tree has a maximum up to 3 nodes, that's referred to as a different term. I think it's a ternary tree, but you'll see a little bit later on. If it has a maximum up to 4 nodes, then it has another terminology, 5 nodes, 6 nodes, and so forth. So those sorts of terminologies are what you're going to have to watch out for, in particular when you're dealing with. So you will always want to ask, okay, for any node, what is the maximum amount of children it can have to determine, okay, what type of tree you're going to be dealing with. And typically we refer to these as an n-array tree. And it's going to be dependent on the maximum children any node has. So, and a good example of this will be the ternary tree, where 3 children maximum it's going to be to any one parent node that we may encounter. Now, because this is the maximum, this does not mean that all nodes will always have 3 children. They can have up to 3 children. They don't necessarily need to have the maximum as required. And a good analysis of this here is that if we watch our root node and we see how many maximum children it has, we see here that there's 1, 2, 3 children. But then for each following node, like for example 4 here, this only has 2 children, 6 has none, and 10 only has 1 child. So we want to see like what's the maximum amount of children one node can have to determine what type of tree we're going to be dealing with. And that gives us the idea of what type of tree we'll be encountering and how many links you need to form regarding the operations of the tree as we keep on going forth in this lecture. Now, let's say if you try to use a tree to represent a bunch of phone numbers, and we can basically see, like, for example, I hope no one dials this number. I'm not even sure if it's still in operation. So 1-868-653-0777. Someone may actually realize this was the number for a popular fried chicken restaurant locally here. But what we can see here is that this is 1 digit, this is 3 digits, this is 3 digits, and this is 4. And if we add them together, we see that basically it gives 10 digits, right? So any international number that you basically dial will basically have 10 digits regardless, with the exclusion of any weird international codes except for this one, like some cases might have dial 11 and so forth, but we're going to be ignoring those for the time being. So we may end up using a ternary tree, where each one of these numbers here can actually be represented as nodes in our tree itself. And each child node would be a digit of this phone number that we had. The end of the number would be the last digit that we have here, and this would actually be a leaf node, signifying the ender as a result. So, to give you an idea of what this can physically look like, I'm not going to draw up the entire thing because I literally physically don't have space on the slide here to draw it out. It would be like if we say, okay, all international numbers must start with 1. And then we can be like, okay, it can be 8, and then this must go 6, and this can go 8. And let's say if we need to dial another international number where the code started with 9 instead, to a 9, 1, 2. Let's say if we are still dealing with an international code of 8, we'll go 1, 8. But then let's say it was 7, and then 6 here, and so forth, and it keeps on spanning like that as we keep on going. Now, there is a difference that we need to distinguish between a binary tree and a binary search tree. So, a binary tree is where it's defined such that any node has a maximum of up to 2 children nodes, but it does not specify anything regarding the order of the nodes. So a binary tree is basically where the nodes can follow any order throughout the entire thing. A binary search tree, on the other hand, is where the order is specified regarding how the nodes are to be laid out in the tree. So what we saw at the start of our lecture, where we had the left subtrees and the right subtrees, where everything left hand was less than the root node and everything right hand was more than that root node, that actually was an example of a binary search tree. And that's given by these two equations that we have here. Basically, all left descendants must be less than or equal to the end node, which is basically your root, and anything on the right hand side as a result must be more than that end node as a result as well. And this must hold true for every node n in our tree. So, hold time. Which one of these trees is a binary search tree? Left, right. And ask this once the poll comes up, and let's see how you guys respond. Alright, get your votes in now, and let's see how you guys respond regarding this. Alright, 15 more seconds for voting. Closing off the poll now. See our results momentarily. Chat. Alright, so the majority of people voted for left, and yes, the left tree is a binary search tree, where the right tree here is just going to be a binary tree. And the reason for this being is, if we watch here, 12 and 10 here, they don't match up regarding our rule here, but the left descendants must be less than equal to n less than equal to the right descendants. So this 12 here, if we need to include it, it would come like if we redrew this tree and we had 8, 4, 2, and then we have 10, 12, and 20 as a result. And then we will have that in a form that it can be said that that's a binary search tree as well. So you need to pay particular attention to these sorts of things when you're identifying a binary tree and a binary search tree as a result. Right. There's also, let me go back. Right, okay, yeah, I'm on the right slide. There's also another terminology that we need to pay attention to, which is referred to as balanced and unbalanced trees. And we watch the height of the tree here in order to figure this out in particular. Now, a balanced tree would be where the height of the left and right subtree of any node will not differ by more than one level. If they do differ by more than one level, then you have an unbalanced tree. So a good idea of this is that let's watch on the left hand side here, which is a balanced tree, and then we're going to work on the right hand side here, which is an unbalanced tree, right? So df here is going to be the difference in our levels as required as we're going to be operating. So 1 here is our root node, and then we have our left subtree and our right subtree here from 1. The difference between the left subtree and the right subtree here, if we watch at this level here, if we consider this level here to be our 0th level, because we're dealing with the subtrees, we can see here that the difference here and the difference here will not differ by more than 1 as a result. So we're basically okay regarding this. However, when we go to our unbalanced tree, and we're going to be watching our left and right subtree as a result, and we're going to be watching here, here, and here. If we're on the same level, there's no difference. But when we go on different levels, then we're going to see that, okay, here it's going to be a difference of 1. But then if you go from here to here, that's going to be a difference of 2. And as a result, because we have that difference of 2, this tree here is unbalanced. So that's what we need to watch out for regarding our analysis here for balance and unbalance. Because if this here is going to be, let's draw this here, our left subtree, this here is our right subtree. This here can be at, just basically say that's level 0, level 1, and level 2. Because our right subtree here is at 3, is at level 0, and our left subtree here can go down to level 2, this tree here is unbalanced because of that difference in levels. So that's what you need to pay attention to when you're describing your balanced versus unbalanced tree. Any particular questions regarding this? Ask now. Alright, doesn't seem like we have any particular questions. Alright, let's go on. So, a complete binary tree would be where every level of the tree is going to be fully filled with its maximum amount of nodes except for the last level. All leaves do not necessarily, yes, all leaves, no, actually, sorry. It's not necessary that all leaves will have a difference factor of 0. The difference factor of 1 in some cases here, what you're seeing, is basically represented between two connected nodes. That's why I did the analysis independent of the connected nodes. So it's like saying, okay, from this node to this node, there's going to be a difference factor of 1. From this node to this node, there's going to be a difference factor of 1. But from here to one of these other nodes here, that's a difference factor of 2 and so forth. So you can ignore these difference factors here that are annotated. The explanations I gave you is actually the more concise way of actually doing the analysis. Because you're going to be focusing on the left subtree and the right subtree in order to do the analysis. And the reason why we say subtrees here is because, remember, this makes reference to your start node. Everything on the left of the start node is going to be the left subtree. Everything on the right of that start node is going to be the right subtree as a result. So don't worry too much about these difference factors here. Just worry about the difference in levels between the left subtree and the right subtree as a result. So a complete binary tree would be such that where we have every level of the tree except for the last level will have the maximum amount of nodes that's allocated towards it. I'll explain a little bit why all these will not have a difference factor of 0, because I'm going to have to illustrate that coming down to the end. So, hold on, empty pool here, ignore those. Take there. Get this up. Alright. Looks like my mouse is misbehaving. Alright, give me a second, guys, just technical difficulties. Alright, there we go. And that's alright, okay. Alright, so I went by with the poll here because I'm having a little bit of technical difficulties with my mouse. So basically, if we watch on this slide here, on the left-hand side here, we can see that if we try to analyze it, this left tree here is going to be a complete binary tree. 10 here has our nodes here in 5 and 20. And then we have 3 and 7 here, and 20 going on to 30. And we may think, okay, this is going to be a complete binary tree. But in reality, it's not complete. Because remember, the definition is it needs to be fully filled left to right, except for the last level. So we need to make sure that left to right order is satisfied. So this left tree here is not a complete binary tree because it does not go from left to right when we watch node 20 here. It goes right and there's no left node as a result. If we watch the right tree here, this is a complete binary tree because it follows the left to right order. Because we have 10 here, then we have 10 having the maximum amount of nodes, 5 and 20, being 2 nodes here. And then 5 here goes to 3 and 7. Okay, that's good. 20 here goes to 15, but it follows the order left to right as a result. So because it follows this left to right order, and the last level here does not need to have the maximum amount of nodes required, this here on the right hand side is an example of a complete binary tree. This here on the left hand side is an example of an incomplete binary tree. Any particular questions regarding that explanation? Right. The right tree here is complete because we need to make sure that for a complete binary tree, we need to make sure the order goes from left to right as it's being filled. So the right tree here is completed because if we watch 5 here, we have 3 on the left hand side and 7 on the right hand side. Same thing if we watch 10 here, we have 5 and 20. This being a binary tree, that means the maximum amount of nodes, 2 except for the last level here. And then if we watch node 20 here, it needs to go left to right for its children nodes. So the left node here is 15, but it doesn't have a right node. So that's okay, because it follows that order left to right. So yes, 3, 7, and 15 here will be the last level. But what we need to pay attention to is the order at which the level here is being filled. And it needs to be filled from left to right from its parent node. The reason why the right hand side here is the left hand side tree here is not filled from left to right is because if you watch 20 here, instead of this being filled left first and then right, it fills right first and there's no left. And because that order is not maintained, the left tree here is not a complete binary tree. There are multiple ways to take attendance online, but it's also understood that some people may not be able to physically attend because they may have other responsibilities. So the metrics also show when people access the replays afterwards, so they still attend the class in some form or fashion. Alright. So remember, the trick to identifying a complete binary tree is that you need to make sure that the nodes are filled from left to right from their parent node. That's what you need to pay attention to. Also, you also need to make sure that at any level before the last level, being the leaves of the tree, that each one of these nodes here basically have they're fully filled. So like if we start at the root node here, we need to make sure that this root node here has 2 nodes for it to be a binary tree. And similarly, if we had an additional level here, each one of these nodes here needs to also have 2 children as a such until we actually reach that last level as a requirement. But the order of which it's being filled from left to right, that's important for you to identify if it's a complete binary tree or not. Right. A full binary tree would be that every node has either 0 or 2 children. You can't have a node that just only has 1 child. So, alright, let's see if my poll here, if my mouse here is behaving. Alright, nice. It is behaving. So, which one of these is full binary tree? Left. See? Alright, we got a poll there up. Let's see how you guys respond. Votes in. So a full node is basically, in the case of a binary tree, a full node will be such that if that's the parent node, it contains the maximum amount of children nodes that it can have. And because it's a binary tree, the maximum here is going to be 2 nodes. Yes, it is based on the type of tree. So, for example, if we were dealing with a ternary tree where we can have a maximum up to 3 nodes, that's what you have to pay attention to. But we're keeping our discussion simple and we just stay into binary trees. So yeah, a binary tree, for the node to be full, it must have the maximum amount of children nodes, 2 nodes. If we try to draw like a ternary tree or a ternary tree or something, we basically are going to run out of physical space in drawing this. And we try not to go on and on about this because, like I said, it takes very long to draw these out. So once you understand the terminology for one tree, you understand the terminology for all. Same with all the operations and so forth. So yeah, that's a nice explanation where binary must have 2 children to each node and ternary must have 10 children to each and so forth. But remember, this is a maximum of. And if you're talking about a full node, then you're actually having those maximum amount of children. Alright, 15 more seconds for voting. Closing off our poll now. See how our results are in a little bit. Alright, so once again, the majority answer is correct, where the right tree here is going to be a full binary tree, and the left tree here is not a full binary tree. No, not necessarily. Tree children does not have to be the maximum if we can have grandchildren and more levels. It does not absolutely have to. Depending on the type of tree you're dealing with, then it may have to. So like for your complete tree, this will be the case. And for a full tree, yes. But for other types of trees, no, that's not necessarily the case. So if we analyze our left tree here to see if it's a full binary tree or not, we can see 10 here has our 2 nodes, okay, that's fine. But then 5 here only has 1. 20 and 20 has 2 nodes here. So that's good. That's good. But this here is wrong. And then we see that 7 here has no nodes, so that's okay. And then 3 here has 9 and 8, which is okay. So these are okay. These are okay. This is okay, but 5 here only has 1 node, so that's wrong. So that's why you know that this is not going to be a full tree. On the other hand, if we watch 10 here, 10 goes here. If we watch our right tree here, sorry, 10 goes 5 and 20, so that's okay. 5 has no nodes, so that's okay. 20 here goes 3 and 7, so that's fine. 7 here has no nodes, so that's fine. And then 3 here goes 9 and 18, so that's fine as well. And 9 and 18 has no children, so that's fine as well. So this one is okay. This one is not because of that 5 node here only having 1 child. Alright. So a perfect binary tree would be basically where you have a tree that is both full and complete. And it being full and complete, this means that all the leaf nodes will be at the same level. And this level here with all the leaves here will be the maximum amount of nodes that you can have. So you will not have any node here before your last level having 0 or 1 children. They will have the maximum amount of children nodes that can be allocated to them. And only at the last level, we will have no children nodes as a result for this particular last level. So a perfect binary tree would be, a good example of this would be that if you have a tree that is both balanced on the left and right hand side with the amount of nodes they do have. So they span accordingly in regards to your 2 to the power analogy. This will be like 2 to the 0, which is 1 node, and the next level will be 2 to the 1, which is 2 nodes, and then the next level here will be 2 to the squared, which is 4 nodes. And if we went down to another level, this will be 2 to the 3, meaning that there must be 8 nodes as a result, and so forth. So that's a good way of identifying a perfect binary tree. Now, in traversing your binary trees, there are going to be 3 types of traversal that you need to pay attention to. And typically, when you see these traversal methods, they are always implemented using recursion because it's easier to implement this recursive techniques than an iterative technique. And it also helps because in an iterative technique, you're also going to have some knowledge of how much depth the tree has. Whereas in the recursive technique, you don't need to have this knowledge beforehand, and you can actually just rely on the recursion to actually figure this out for you as a result. So the in-order traversal is that where we go such that we visit the left branch, then the current node, and then the right branch. And as a result, it visits these nodes in ascending order. Now what we're going to see here is that we have the in-order traversal code. These 3 lines of code here are just going to be reordered for each one of these traversal methods. And all we just need to basically know is what's going to be the order for each one of these. So in order goes left branch, current node, and then right branch. And it does this in ascending order as a result. Pre-order traversal is that you visit the current node before its child nodes. So you start with your root node, and then you go to each one of the child nodes as a result. So it will be such that if I illustrate this, we'll be at this here being our root, and then we'll go down to the left tree, which is going to span like this. So we go this way, and then this way. And then from the roots, we go on such that it's going to be down to our right nodes. So we'll go this way, and it'll go this way as a result. So it's just going to be a little bit different regarding these sort of nodes, how you go about visiting. So this is how pre-order traversal will operate. And as you can see here, these nodes, how they are visited, the order of the operations here just change for pre-order traversal. So we see visits, and then node left, and then node right. But in previously, when we had in order, we had left, then visit, then right. So because we know that the order of these operations here just change for each one of these traversals, post order will just be left, right, and then visit. So it will be such that we are going to be visiting the current node after its child nodes, but we are going to be visiting the root node last as a result. And it's just basically, you just change the order of which these operations just run to get these different types of traversal. So are there any particular questions regarding in order, pre-order, or post-order traversal? Alright, doesn't seem like we had any further questions regarding that. Alright. Now the last thing that we need to pay attention to here is something that we're going to refer to as a binary heap. And they're also referred to as minimum heaps or maximum heaps. So we don't need to know both of them, because basically a minimum heap is just going to be the reverse order of a maximum heap and so forth. So a max order heap, or a maximum binary heap will be such that the elements would be in descending order. But for a minimum order heap, the elements will be in ascending order instead. So a minimum heap will basically be a complete binary tree that we're going to be observing, where each node is always going to be smaller than its children. And as a result, the root node will be the minimum element possible within the entire tree. So a nice example of this is that if we watch here, and we watch all the children nodes because they're going from the children nodes up to the roots, you see that, okay, it's going to be 55, then 90, and 87. 55 and 90 here follow the order such that the left side of 50 is such that, sorry, I'm saying this wrong. This follows a complete tree that we basically see in here. So we can basically see that we have the biggest values here at the base, and then the smallest values as we keep on going on upwards throughout the entire tree. And there's going to be two key operations for the min heap, which is going to be the insertion of a node and to extract the minimum value. And we basically can see here that the extraction of the minimum value is going to be quite easy because the minimum value is always going to be the root node of the entire tree. But insertion here is going to be a little bit tricky because we need to figure out how do we insert this node and we place it accordingly in our minimum heap tree as a result. So in inserting a new node, we always start at the bottom of the tree. And we always start at the rightmost spot in the tree to maintain the property of the tree itself, meaning that it's a complete tree. Then, in order to make sure we figure out where this node is going to be placed, and in order to maintain the ordering of the minimum heap, we keep on swapping the new element with its parents until we find the appropriate spot where it actually needs to be. And the entire runtime of this is going to be of a log n complexity, where n is going to be the number of nodes in the heap itself, until we actually find the actual spot. So, for example, if we had that same tree here and we inserted node 2, it's possible for us to go about swapping this until we figure out, okay, where does node 2 need to be in the entire tree? Now, at a simple glance here, because we can see that 2 here is going to be less than our root node, we know 2 needs to go on top here as a result. But in shuffling these nodes, what's going to happen to these nodes that are in order for 2 to be swapped accordingly as a result? So, because 2 here is on the rightmost side because of our insertion, and we need to swap it with our parent node because it's less than the value of our parent node, we do this swap here first, so we such that we swap 2 and 7 here as a result. And then we do a comparison here with 2 to our next parent node, and we see, okay, it's still less than. So we do the swap here again, make sure that 2 goes on top here as a result. And then finally, we can just do a general check to see, okay, is 2 less than any previous values that we have? Was it at the root node level? And then we know to stop swapping, and we've maintained the order of the tree as is throughout the entire thing. So the insertion for the minimum heap will always follow these general steps. A new node will always be inserted at the rightmost possible spot in the tree. And then depending on the value, it's going to be swapping with its parent node in order to make sure that it maintains this order throughout the entire tree for your minimum. Are there any particular questions regarding the insertion of this node for our minimum heap tree? Alright, doesn't seem like we've got any questions regarding the insertion part. Alright, let's go on. So extracting minimum element is always easy because it's always going to be at the root node. But in removing it, we need to also make sure that we follow these order of operations here to maintain the order of the tree. So once we remove that minimum element, we need to make sure that we maintain that order of the tree here by finding what's going to be the next minimum element as a result. So we'll start with swapping with the lastmost element in the heap being the bottommost rightmost element. And we keep on swapping this until we maintain the order of the min heap property. And if we ask which one of the children nodes that we need to swap with as we keep on going, we're always going to be taking the smaller value to maintain that min heap order. And we get a runtime of log n as a result as well. So a nice extraction here would be such that, okay, we had 80 here to begin with, and we need to get to this replacement after we did some extraction on top here. We need to make sure that we do the swap here accordingly until 80 goes into its correct position as required. So we watch 50 and we watch 23. 23 here is going to be the least value. So we do the swap here accordingly to get this. And then we watch 32 and 74 here. 22 is going to be the least most value. So then we do the swap here accordingly. So we want to maintain that minimum heap property as a result. The last sort of data structure that we have to deal with trees is also referred to as tries, which is a prefix tree. This basically deals with characters instead of numbers, where each part down the tree may actually represent a word in a dictionary. And tries in particular are useful for dictionary lookups, especially when you're trying to watch for any particular words that you may be trying to predict or and so forth. So that nice word prediction that you have anytime you're doing some sort of Google search, the basis for that actually is a prefix tree or a try for it to try and predict what you're trying to type. And the implementation is it uses a special type of node, or it uses a type of Boolean flag within the parent node to figure out, okay, where does we go about finding out what you're trying to type. So, like I said, tries are basically used for like your predictive texting or your predictive languages, such that it tries to figure out what word you're trying to basically type in particular. And it uses hash tables to speed up its operation to see if it's going to be a valid word or not. However, it cannot tell us if the string is a prefix of any valid word before that. So unless these words here are basically in order as required, it cannot tell us if that word there is going to be valid as a result, unless the tree actually has its order in to be set. So tries basically allows us to do predictive texting a lot faster because of how the tree is layered and operated, as well as it reduces the amount of data that we actually need to go about sifting throughout. So that way it just keeps on using less and less data as it goes downwards. And the runtime is linear, where k here is going to be the length of the string that we're trying to type. So for your homework regarding binary trees here, and you know why we have certain types of homework here to give you a head start on certain assignments. So you want to make sure that you want to figure out how a max heap would work, and you need to explain the operations and the methods for these in particular. And you're given the binary tree code on My Learning to start with, and to see how it actually operates and how it actually works. So for each one of those functions in that binary tree code, you're going to need to write a short description of what the function does and how it operates with respect to the nodes in the tree. And you may also, in some cases, have to provide a visual aid to go about explaining these operations. And that's going to be somewhat of a big hint regarding one of your assignments. So you may need some visual aids for some of these functions. And this lecture did already cover some of these functions as well. So you actually have some of the information here beforehand before attempting this. Alright, so that basically brings us to the end of our trees lecture. Are there any particular questions before we move on to graphs? Alright, it doesn't seem like we have any questions regarding trees here. Let's go on to our next lecture. Graphs.